Raghuveer is a postdoc at Italy, Florence, and he got his PhD in Bonn, and then he was at Brussels, so I'm doing better today, right? And he gave a colloquium overview talk yesterday of the many things that he has worked on dark matter with many themes. Today he's going to be focusing on the condensed dark matter.
Thank you. Thank you for having me. So, as the title suggests, I'll be talking about condensed dark matter, the Yukawa interaction. In other words, we want to look at dark matter in the strong coupling regime, but still perturbative in some sense, and try to see if there could be some emergent phenomena that can arise in the dark sector. We have evidence for dark matter over various scales, from cosmological scales to scales of galaxy clusters to the scales of galaxy. And all of this points to some sort of a non-luminous matter that is, it has very weak couplings with standard model particles, and the biggest problem in this business is we do not know the mass scale, and that's a free parameter for us, and we would like to see how that plays the role. So, similar to dark matter, there's also normal matter, and we know normal matter exists at various densities. Like hydrogen, water is like gram per centimeter cube, and neutron star you can be as much as 10 to the 15 gram per centimeter. This is like nuclear densities. Now we can also envision that much like standard model particles, which are asymmetric, in the sense that only protons in abundance and not antiprotons, dark matter is also asymmetric. If that is the case, then it could be that similar to normal materials, can exhibit similar features. And the most important point, the factual point, is that dark matter also exists at various densities, particularly in the Milky Way dwarfs, about 100 GeV per centimeter cube, with the dark matter particles in neutron stars, about same 10 to the 15 gram per centimeter. Our GeV is 10 to the 23 GeV is a gram. That's right.
The Q itself,
yes,
it's supposed to be 1 proton per cube. That's the 1 GeV.
So the critical density of the universe is about 1 proton per meter cube, and cosmologically, the dark matter is at least 5 times as abundant as normal matter, and the same holds for Milky Way, because we are in collapsed structures. Dark matter density is expected to be larger on those things. But
so these average density.
These are average densities at this particular position.
At the position, very large,
yeah,
maximum.
So I'm not
maximum in the white dwarf. Dwarf.
Yeah. So
dwarf.
So this is a well-known number.
Halos.
Yeah. In the halos of major dwarf galaxies, this is a well-measured, undisputed number. But within the Milky Way itself, there is some dispute about what is the central density, because lack of data, difficult observation, because we are sitting inside the world. Okay. So what I'll talk about here is that putting in the facts, or putting two things together, that is, dark matter exists at finite density, dark matter is asymmetric, these are the assumptions, and we introduce a very simple Yukawa interaction, the simplest of interactions we can make.
The dark matter is asymmetric. So how do you know that it is asymmetric?
We do not know. It's an assumption. So, as I said, analogous to the standard sector, there are more protons and antiprotons.
Is there any motivation for that? Like why there should be some, like in standard model number, there is 50-50
So there are baryogenesis mechanisms that could be linked to dark matter as well. The same mechanism that produces asymmetry in the standard model sector can also do it in the dark sector. So it's about how you complete your UV.
Oh, so then the coefficient theory already has a dark matter candidate.
So okay.
Also standard model.
So standard model plus dark matter. Let's say my UV is very symmetric, but then there is a mechanism, maybe some heavy like a leptogenesis mechanism, that also produces asymmetry in the visible sector and dark sector. So you just take the standard vanilla leptogenesis and add dark matter with similar coupling structure. You'll get the same. You'll get similar asymmetry.
but then the constraints here we clearly do.
So with visible matter, there is evidence, as in there is a measurement that shows this asymmetry, basically from ppm. Baryon to photon ratio is a very small number. From that, that we know it's asymmetric. But there is no such measurement for dark matter. So that's the freedom we have in this sector. This is an assumption. And why I say asymmetric, because if I put many particles that can annihilate at large densities, they prefer to annihilate than just stay there. So to stop the annihilation in late universe, like today, I'm assuming it to be asymmetric. So I can maintain finite density. That's
The CP violation is very crucial from this asymmetry.
yeah.
Whatever is source for CP violation should be affecting dark matter. So now,
Yes,
assumption.
that's an assumption. Yeah. So that's a different.
Unless you have a new mechanism for CP violation for dark matter alone.
Yeah. So there are n number of ways where you can arrange this, but that's a discussion on its own, as in what are the possible ways. And
You are putting the extra thing as part of a beyond standard models already, or it's a new one?
so what I'll talk about is simply it is beyond the standard model, because I'm already assuming dark matter is a particle, right? And on top of it, I'm assuming dark matter interacts with itself through scalarity. So I'm adding two new particles on top of that. But the thing is that they do not see the U1, they do not see any photon.
It's hard to build insights to clearly or linear.
But this is a low energy description. These description can always be mapped onto some such manifestations. That's a topic.
Give a statement. Dark matter is a particle.
Yeah.
It is not a particle. What means correct? Photon is a particle.
So primordial black hole is the other candidate for dark matter.
Oh,
Yes. Any, but they are massive objects.
They are massive horizontal objects. That's another alternative.
Primordial black hole.
But primordial black hole as a dark matter, it cannot be more than 1% or
that is
10%.
probably ruled out already,
No,
It is
it's-
already ruled out by
unless something else is happening.
no, it's a mass dependent statement. You say,
Sorry, can I suggest that you come back to this thing if it's not central to your talk?
okay, yeah. Primordial black hole is not central to this talk.
Okay, sure.
But
So
this,
and maybe in the question.
Sure. No, I'm just saying that many things prefers that it is a particle, so it's.
so particle dark matter is the most economical solution that can answer
Yeah.
all these things at different scales.
But what about ultraviolet dark? Is it a particle or a wave?
Well, it is a particle. It can have a wave description. No problem there. Okay.
So Raghuveer, just move on, we'll come back to it.
Okay. So what I talk about here, so often asymmetric dark matter has been discussed in literature for the past 20 years, but what I talk about here is with interaction and with emergent phenomena in the sector. And this emergent phenomena is often talked in the context of bosonic dark matter, but that's an effective theory and I will not be going into that. So the speciality here is fermionic dark matter at finite density. So what I will show you is phases of Yukawa theory in this dark sector and various in-medium effects that arises at finite density akin to standard sector. And finally, using these machinery and what I will and the setup, I discuss about equation of state of dark matter and its implications for dark matter halos and such. So that's the deep outline. So what is the model? The model is very simple. This is my fermion psi, which is dark matter, couples to a mediator, which is a real scalar phi, to a Yukawa coupling, and I put it at finite density. So simplest model, four free parameters, masses, coupling, and the density. Chemical potential is a proxy for a number.
You don't have a metric. It's still
So I'm assuming FRW. Yeah.
FRW or
As in, this doesn't enter here. All of this discussion doesn't enter here. It's not at all relevant. But this is in an FRW universe. If you want to think about production. So just from the construction, they're all singlets of standard model sector, and dark fermion here has a global dark number conservation. So for what follows, Fermi energy, and I use Fermi energy and chemical potential interchangeably, and they are related to the masses and Fermi momenta. This way is the usual dispersion relation, and the number density n, which is the conjugate of the chemical potential, is psi bar comma 0.
This mu parameter also regulates your asymmetry you stated in the beginning.
It's a free parameter in the
So
sense.
it may be a free parameter, but as soon as mu is non-zero, you are preferring matter over antimatter and vice versa, right? Depending on the sign.
So this is a late. Yeah, you can think of it like that. Let's say I take.
But this is dark sector, right? This is not our matter. The
Yeah,
size
I
of-
understand that.
It's a chemical potential.
Exactly.
Particles.
Yeah. So it's basically energy it costs to pull a particle out of a thermal bath. My thermal bath here is just consists of these particles.
You are doing this in G plus not G.
G plus 1.
But you have a sign problem.
Sign
Finite density calculation. Right.
sign problem where.
The cell rate.
No, he's not doing numerics.
See, even without numerics also, the Lagrangian is complex.
Right. Then
If you want to do path integral, then in the path integral you have complex rates.
you have Grossman variables. But sine
So no, wait,
comes-
I'll come to all that. I'll introduce auxiliary fields. I'll use Hubbard-Stantanovich to do all this. So we are aware of that. I just didn't know it was called a sign problem. Okay. Okay. So just a small comment. So the story is already well known in QCD. So the simplest way is that this psi bar psi phi can be thought of as one gauge boson in the QCD sector, just one gauge boson that can be. So the decomposition here it goes this way. And all this emergent phenomena, in fact, exists in QCD, mostly because there are two light flavors and there is an antisymmetric channel which is attractive. So that's the analogy to QCD. So this often in QCD, this often goes in the name of color superconductivity and so on, that in principle is possible inside neutron stars, but we don't know yet. But the idea or the physics behind it is very similar, but it's much more simpler because of the structure, that structure.
So if I remember correctly, years ago, colleague here, Raghuveer and company, they also talked about pairing of neutrinos
Okay,
in the context of
so neutrinos can bear, sure, but
neutrinos.
neutrinos are not dark matter because their energy density is much smaller than expected.
Vaguely remember.
But because neutrinos in principle can also exhibit this, then there's nothing stronger.
But if the neutron star densities are not
So-
high that it goes to the color superconductivity.
So that's the debate. So if you find a neutron star tomorrow, which is more compact than what we have seen today, then this could be realized. So this is a theoretical game. So in principle in QCD it's possible. That's the story. Okay, let me. So I started out with the Lagrangian, and what I want to show here is even the simplest Lagrangian, you can have different phases of matter, and often you can hear. Often this is BCS, Body-Cooper-Schrieffer, which is source by an attractive interaction, and the Bose-Einstein condensation. So in the BCS phase, basically it's like two particles separated by a distance, but they move together the same way. That's BCS. But BEC is more like a molecule. You interact so strongly that two particles behave like one. So two particle bonds. And all of this is well
So
understood.
these are charged particles.
There is a global dark number.
But in the Lagrangian, you didn't write
So scalar exchange is always attractive.
Captain.
Okay, that's the, so you don't need to charge as such. So it always sources an attraction.
But you have a conserved number, psi bar gamma psi. It's a conserved number.
That's a conserved number, but it's not gauged or anything. It's just.
No, that is the this is the one you have typically.
Yeah. So a conserved number, basically it's a conjugate of the chemical potential. That's about it. So to understand the phases, at least in dilute gases in the non-relativistic limit, we just can compute the scattering length at, in this case, at finite density. And that's what I will show you. This is very similar, again, coming back to analogy with QCD. So people have thought about this much more than the Yukawa theory, although it's way more complex, but it is by reality. So what I will discuss for the Yukawa theory is really equal to 0 and as a function of chemical potential. So on this plane, I'll be on just on the axis. I just show this plot here because just because of the structure of QCD, you have way more complex phases that you can expect here. But as I will show in a Yukawa theory, there are still phases, but they're much simpler.
So when you say BC, what do you mean superfluid or BC?
No, BC, I really mean a BC, but it can be superfluid. I'm not going there. Probably I'll go there.
You don't know the dispersion.
Yeah, I'll come to that at the end. But when I mean BC here, it's simply a molecule, two particle bonds, like deeply bonds.
This dark matter you're considering, where is that? Is that in the halo, galactic halo, or like condensed objects?
So physical picture we have in mind is really dark matter particles in the halo,
Okay.
and these particles are at finite density. So,
But is it a good approximation to say that it's at zero temperature?
so
It's not.
it's not. So the thing is, the temperature, velocity dispersions are a proxy for temperature, and given velocity dispersion, which is about 10 kilometers per second in warp galaxies, it's somewhat a good approximation, at least theoretically, to first do the T0 limit.
Okay. It won't upset things that you will say.
It won't qualitatively change things. Quantitatively, things can move left, right, or up, down, but qualitative behavior remains the same.
What is the typical value of the chemical potential is much larger than the temperature?
Yeah, that's the standard limit.
Because that's why your Fermi surface is big.
It's more like a sharp theta function, very small deformation.
And the non-zero mu is important for your case.
Non-zero, why?
Yeah.
If I don't have non-zero mu, I'm not at finite density.
Well, standard WIMP, you can think of it zero mu, right?
Yeah, but you won't exhibit emergent phenomena. So you refer to, by the time you begin to exhibit emergent phenomena, you might just annihilate it. That's what happens.
But if it is like standard WIMP, we know it is not annihilated, right? Because of some conserved global charge, like a Z2 charge.
They do not
It is
decay.
zero mu, but there is
No,
some
no, no.
conserved.
Z2 just tells you will not decay, but you can annihilate.
But we know standard WIMP has not annihilated away because of freeze out, right?
Yeah. But
That will not give you any of these phases.
because indirect detection, if you think about it, it's about dark matter annihilation in galactic centers. And there WIMP is annihilating,
Yes,
but at a different rate than in the other,
yes.
controlled by density.
Yeah.
So now if you are at finite, if you're asymmetric, that means you just chop off the annihilation. And there's a buildup of density.
Yeah. No, I mean, if it is in the gravitational potential, there is a buildup of density purely due to gravity. That's the halo, right?
Fine.
And the question is, are the densities there big enough that you can see these phases?
No,
Even without any AC.
No. They will exactly.
Like WIMP, I'm thinking of WIMP. They have not gone away, right?
So WIMPs have not gone away, but
Yeah.
they're slowly annihilating. It's like
That's okay. There is a small residual annihilation, but that should not upset your phase.
so. The phase of matter for WIMP
Yeah.
is not BCS, not BEC. It's
That's right.
non-relativistic dilute gas.
That's right.
That's the phase.
So the question is, without any asymmetry, can you still think of these non-trivial phases? No.
Very difficult. I wouldn't think so.
It's not clear to me. Maybe we'll talk later.
So there is no well-defined Fermi surface. So you do not know. So you cannot say anything. So okay, coming back to phases. So we find that there are three phases which we can compute just by solving the Schrodinger equation in the non-relativistic limit, but at finite density. And this is captured in terms of this dimensionless parameter alpha m over m5. This is, if you remember, hydrogen atom or sort of hydrogen atom. This is like range of mediator divided by the core radius of the would-be molecule. And the y-axis is simply the range of interaction, ratio of the range of interaction to the size of the thermosphere. So how much you can deform the thermosphere from long. So at small values of beta, we find that we are in the BCS phase, that is scattering length is negative. And as we increase beta, you encounter a BEC phase where the scattering length is positive. And at some point you cross over. So I put -1 and 1 here, just by the intuition here is from experiments in the lab where they see -1 and 1 to be reasonable parameters to capture these phase boundaries. And at some point, if you, let's say we start here at beta equal to 1, I start increasing the density, that is, I keep adding more particles. From the BCS phase, you transit to a crossover. That is some sort of a mixed phase where crazy things can go around, but our calculations are not under control. So that's how one called a crossover.
So this alpha is the Yukawa coupling.
It's G square of the Yukawa divided by 4 pi.
So Yukawa coupling, the mass of psi and mass of phi.
Yeah.
These are the three parameters.
Yeah, on the x-axis, and the y-axis is the Fermi,
The density.
the density.
BCS phase, similar things happen, like your surface is now getting disordered.
So BCS is a perturbation to the Fermi surface. So a sharp theta function becomes a smoother function.
In normal superconductivity, the Fermi surface is unstable. Here also, similar thing happens.
It's a similar thing, yeah. It's almost the same thing. The only difference is it's a superfluid, not superconductor.
Then here in this phase, the number density will become the phases.
Yeah, exactly. I'll come to that in the more technical.
So then the molecule is psi bar psi molecule.
So molecule is you mean the BEC?
Yeah.
It's a psi psi.
Okay.
So
Yeah,
like
psi, yeah.
I put
This
take
also.
one proton.
Right.
Yeah.
But you have an asymmetry, so you have a charge, right? You can think of it as psi bar psi.
No, okay.
What asymmetry do you mean? Is there a
So
global charge or maybe if it's not
There is no human.
There is no U.
One slide later, it will become very clear.
Okay.
What I mean. So, okay, in
So
the
the
BCS,
crossover is essentially superfluid, is it?
no, superfluid is in the BCS. Well, superfluid can be BCS and BEC, but I'll focus on BCS because I can do the computation more reliable. So, okay.
So it's happening when you go in the horizontal direction.
So, this repeating feature because scattering length is a tangent of the phase shift and the phase shift is changing by pi. That's the repetition. But as you go this way, you go on to something called a classical regime of scattering. That's where your gravity is a classical regime of scattering. In other words, I'm reducing the mass of the mediator. I make it more and more long range. And that means if you have a central potential, the particle comes in and just keeps in an unstable orbit for a long time and scatters. So that's the classical regime. But if you make the mediator heavier and heavier, you are away from the classical.
So I have not seen this gap structure in condensed matter context. Normally you have only absolute.
Yeah.
So you said it's because the phase shift is going around.
Yeah.
Because more bomb states are
More modes.
more bomb states are being done.
Oh, I see.
Because you
So that
increase
means
the
instead
strength
of
of
2,
it.
you have 3 and so
Yeah,
on.
3 bomb states, and next you have the bomb
Okay,
states.
I see. So like molecules and post molecules.
Yeah.
So for that you need to, it's also a density dependent statement. You satisfy large densities, you can form n molecule, n particle bonds.
Here this distinction is just based on the scattering, right?
So yeah, at this point I have not considered emergent phenomena, I mean quantum effects.
I am actually concerned about these things. We go to larger values of k of by or smaller values of beta. Is your approximation of smaller k values, smaller momenta value. You do not have to include higher k square or k terms in the scattering or scattering after expansion.
So for the scattering,
Because in your previous slide you showed that your k is equal to k is equal to 0 limit, you can consider k so that as 1 by n. But it's not necessarily to go to higher values of k.
I agree. So especially if you are about 5 years,
Not even 5 actually, even if you are at 1, it is already there.
it's on the edge. Here it's on the edge, I agree. Indeed, it will become relevant. And in that case, one need to consider the effective range of block connection, for example, for the cross section of the amplitude. That I will not discuss here, but probably at the end, I will say how I can use it to put some limits. But it's a valid concern. So I would strictly trust this plot below about 1 or 2. Above that, maybe it's some sort of okay, but not too reliable.
Is that also not along the x-axis because there are also regimes in the x-axis where you cannot consider 1 by n on the approximation? Because you have this m factor in the beta.
Yeah, so it's very true. So these throats are called, this is where scattering line diverges.
Yes.
And this is where what people call unitary gases, unitary Fermi gases. And all these throats, this happens. And we just see that the scattering length is diverging and we stop there. We don't try to refine it more. We were very happy with this already because we found that people had not discussed the phase diagram of Yukawa theory, but they have done QCD. So it's very surprising. But if you are aware of a work that discusses this, please let me know. And there's one more limit where the scattering then goes to 0. Those are these lines. And these are non-interacting gases. So there's a lot of information just by solving Yukawa theory at finite density from the Schrodinger. So that's the main point. So what I'll talk about now is just the BCS phase, focus a little more on the BCS phase and see what it means for equation of state of that. So if I have a degenerate medium, they're only strictly degenerate, mu over t is very large. There are only 2 possible scattering possible. One is totally forward scattering, that is particle stays there, can get some quantum correction, and a backward scattering. And backward scattering is here a scattering between particle and a hole. So that's why I have a conjugate. So this is nothing but the superfluid gap. And in the BCS phase, these are the 2 quantum effects. So this is a perturbative effect, this is a non-perturbative effect, and this has to be considered just to make solid statements. So fully forward scattering. So what does this mean? So simplest sense, let's say I integrate on the mediator, now propagate of this sort, and in big language, you contract psi bar psi. So that means, so this gets an expectation. So at finite density, this is not 0. In vacuum, it is indeed 0. So what this means is that, so this will basically, this is an expectation value times the propagator. So that means psi bar psi in the Lagrangian gets a correction. So it becomes a correction to the mass of the particle. So in other words, it's in words of Voleka, it's psi bar psi, which is the scalar operator, the number operator that gets a non-zero. So this is different from psi bar gamma 0 psi, which is really the number density, but this is really psi bar psi. So this is what gets there. So in the mean field theory, you can assume that the scalar field is non-propagating and find the variation with respect to the Lagrangian, and you find that the well of the scalar field is proportional to the well of the psi bar psi. So the effective mass m, our m star here, is a bare mass minus some correction. And so because all of this quantity here is positive, basically particles become relativistic in the field. So that's the effect of considering this forward scattering. So again, this is nothing new.
So M star is very close to 0, is it?
So it depends on the parameters of the theory, but 0 is the ultimate limit. So you can make it to show that. And this is very similar to Lambo-Journo-Lacino model, where fermion masses are reduced in a medium, but this is in a slightly different model.
Ns is the number density.
Ns is the number operator, psi bar psi, or psi bar gamma 0 psi is another. So I'll tell you why this is important. So psi bar psi, you can just decompose it in terms of creation annihilation operators, integrating up to some chemical potential. You'll see that Ns is proportional to m times the Fermi energy and Fermi momentum. So in the non-relativistic limit, that is when Fermi momentum is much smaller than the mass, the number operator and the number density are very similar. They go as a leading order can be thought of as polar scale. But in the relativistic limit, n still goes as k cube, but ns goes as m times k square. So that's the main difference. So it's a self-regulating theory because ns depends on m. So you have to solve it iteratively to find the value for a given g, for a given Fermi momenta, or chemical potential g and mass of the medium.
So the usual fermion number, global chart, that is which one? N or
n.
And here the chemical potentials are larger than the mass. Unless you have larger chemical potential than the mass, you have some other problems. You cannot excite them.
Yeah. So this really holds meaning when you're in this regime. Otherwise, you can simply
And
talk.
this chemical potential sets also your bound surface.
Yes,
That is what is setting.
that's what is setting the position. Okay. So numerically, this is what it means. So on the y-axis, it's effective mass over the bare mass. So the in medium mass over the vacuum mass, and divided by kf over m. And here I show this for some combination of parameters. Blue curve is the heavy mediator, just 5 times the mass. The red one is half of the dark matter mass, and the green one is 10% of dark matter. And solid and dashed are for values of Yukawa coupling G equal to 3. So let's start with the blue curve here.
A large value of coupling does not disturb your permittivity expansion.
So it's a problem. We need to regulate and renormalize better. We are on the edge here because for us this was a toy model just to push the boundary of the theory, how far it can go and how much we can make sense.
But worried about non-quadratic. After constant.
Yeah. I agree. That is a problem we are aware of and we do not address it here. So
It's reliability of your result.
So G equal to 3, I'll be a bit suspicious myself.
It is a smaller values what stops the results. I mean, you can consider very small values of G.
Yeah.
So that perturbation will what are the consequences?
So
I mean, what
sorry, other way of asking question is if you take small values of G, will your effect go away?
So the largest effect here comes from the ratio of the mediator mass to dark matter mass. And the coupling you see is a small effect. So solid line is G equal to 3, dashed is G equal to 2. G equal to 1 will be slightly over to the right. If I make it even smaller, these curves move to the right. But the sharpness of this, so qualitative features, sharpness of this is really set by the ratio of the mediator mass to the dark matter.
But is it reliable when you have G equal to 3, those two curves? G equal to 3 and 2.
So G equal to 2 is reliable.
So this calculation is perturbative.
Yeah, this is at the perturbative level.
Question will be, is it reliable?
So G equal to 2, I think it is reliable up to order 1 correction. G equal to 3, I'm not sure.
reliability means what actually? That means the higher order terms will
Are
be much
comparable.
smaller compared to this. But how do you estimate that?
So I did not estimate this. The way to do it is to consider, if I go back to,
Sorry, naively it is G squared over 4 pi, right? I mean,
Yeah.
G squared over 4 pi.
so I need to exchange the pi here. I go to another loop and do this thing at finite density. And so I did not do this two-loop calculation at finite density. But the qualitative feature, I think, is the same even if I'm at G equal to 3, up to corrections, which will not change at the falling off part. That's the point. I understand your concern.
Can you show me the previous slide?
This one.
So this NS by M y square. Is order one term or the?
It depends on what you put.
This expansion makes sense only if the additional contribution is small.
So the G square over M phi square just comes from G and F phi here. If I'm talking about higher order terms, so I'll have to exchange, I have to put a line here and do a G to the 4, M phi to the 4. That's the next step, but at finite density. So that term, when G equal to 3 is comparable to, it's not small, that is true. But the qualitative feature that the curve is dipping as strongly as a function of M phi over M remains true. So we are after qualitative features and in this work, but we are working on more quantitative things.
So NS by M phi square is much less than 1. NS by M phi square.
No, not true, no? So Ns goes as M kf square divided by M phi square. I mean, it's not necessarily less than 1, no? It depends on the Fermi moment as well.
So then that expansion which you have given, the correction, to have higher order corrections which will be much larger.
Yes, it will.
That will not affect the qualitative.
That will not affect the qualitative. Quantitatively, it does.
How do you? For
So-
example, if the coupling is large, then you need to take into account all the terms.
Right.
The sum of all the terms happens to be a completely different looking function than the quantitative.
Yeah.
And the qualitative is catchy.
So
A priori, I don't have any.
you also have a loop factor, right? It's effectively D squared over 4 like always, 90, right? So if G is 2, D squared over 4 pi is still 1 over 3. So you still have some perturbative control. If you take 3 as you're saying now, you might really run into problems, right?
1 over 16 pi square.
Yeah, but you take the square root perhaps.
Okay. Yeah.
And then alpha is G squared over 4 pi.
I agree with your concern. We are on the edge there.
2 might be reliable, 3 may not.
Yes.
You have only one scale from problem. This means for KF.
So there are this ratio of masses and ratio of Fermi momenta to the mass. So we present this in dimensionless quantity so that you can rescale it. So G equal to 2, G equal to 1, for example, will move this curve slightly to the left. But the main point is that as I increase my Fermi momentum, the effective mass in the medium decreases. So particles appear to be more relativistic in the medium than in the vacuum. That's the main result of forward scattering. And if you make the mediator lighter and lighter, that is longer and longer range interaction, the onset of when the particle becomes relativistic in the medium is actually before KF is ordered. And this does not change with G equal to 3. Still, G equal to 1 is still a small correction.
The BEC and BCS, that seeing those phases, those persist for small g.
So these are at small g. Yeah. Small
There is
meaning
no
G
real
equal to
reason
1.
why you should take them so large.
There is no reason why, but this is where your effects get, that's the limit now, in the sense.
The effect should be more,
There's nothing driving me to choose that value.
The effect should be more pronounced if you take larger g.
Yeah.
That's which effect?
Actually, if you take the RG improvement of G is going large.
Yeah.
So your perturbation theory has the problems anyway. But G is anyway going to be large. And how you manage is a separate problem.
That's a different discussion. So as I said, the phase diagram depends on combination of alpha and over alpha. I can increase alpha but decrease m. I get the same number.
No, but what is the effect you are after this for orientation? So what would you like to show in the end, that what would happen?
So
and will that persist when G is small?
It will persist. That's what I will show you later.
Okay, then maybe we'll continue.
It will persist.
He's only the 12th slide.
Yeah, so we should, yeah, we should move on.
Okay.
So that's a time to
The seminar coordinator asked me questions and somebody.
So that concludes the forward scattering. Now I'll talk about backward scattering. Backward scattering is really scattering between particle and a hole in condensed matter language. And this is basically what Leon Cooper figured out in 1957. So here what is happening is that an object psi or psi conjugate psi bar is getting a web. And these are at two different positions. And this is essentially superfluidity. In the language of big contraction, you contract the psi bar at x with the psi bar at y, but that contraction is not defined mathematically well, so you write it in terms of conjugate spins. And a conjugate spinner is thought of as a whole because I have an asymmetric. So just to give you the qualitative feature of what this means, let me integrate out phi just so that we come to a familiar four-Fermi interaction, and the Lagrangian just takes this form. Now I can decompose the Lagrangian in terms of psi and the conjugate spinner psi bar, psi c, and this is commonly known as Naumburg-Gorkov space, 8x8 space. So when psi bar c gets a web, you get entries in the off diagonals. That means it introduces Majorana masses at this level. And this is the difference between Prout-Ongley-Higgs mechanism, where you get a mass on the diagonal entry, the Dirac masses. So what superfluidity does, or backward scattering in this language, is introduce Majorana masses. And this changes the dispersion relation. That's how you see the superfluidity. So diagrammatically, it looks like this, and this blob is a non-perturbative effect. This can be solved in various ways. I'll show you in just one. But at least in the limit of heavy mediators, that is when this simply goes as 1 over m phi square always, there's no moment of dependence. You can do a Dyson-Schwinger to do this part of the calculation.
So your Lagrangian had an exact global charge, conserved charge.
Yeah.
So it's really the mu that turns on this off diagonal.
So mu is still on the diagonal.
Okay. Now what happened? The global charge could have prevented the Majorana. Conserved global charge.
So it breaks that global charge, and that is super.
So you have some other, like operator which breaks that charge.
So this one, precisely this one.
Yeah.
Particle hole mixing. That's what. That precisely breaks it.
Which is a finite density effect.
It's a finite density.
At zero density, that will go to zero.
That goes to zero.
Psi C bar
Yeah, psi c.
takes the charge.
So okay. So in terms of dispersion relation, so this is how. So dispersion relation is simply m square plus k square when there is no gaps, or this delta is often called a gap, and then it's linear with k square root, so it's linear. So it just goes like that, particle. But as soon as you have the off diagonal turned on, when it gets an expectation value, dispersion relation changes. You get a plus delta square, and that changes. That creates a gap or a band gap. It's recycled in many ways, and what this does is basically at large momenta it pulls it down, and this is known as particle hole mixing. And this is basically, so this delta is really the gap from the previous Fermi surface to the new. It is also known as the order parameter. There are many names for this. So that's the qualitative thing. Now I'll show you how we do this calculation. So how much time do I have?
Actually, maybe 15 minutes.
Okay, I have to
Or
hurry up.
20 minutes.
Okay. So the way you do this business is that we don't know what is psi bar c. So you need to assume an ansatz. First you assume an ansatz, do the calculation, put it back in, and see if it's self-consistent. So what Bardeen, Cooper, and Schiffer did was assume gamma phi ansatz. So the only restriction here is it should be translationally invariant in the system, and you do the functional approach. Basically, you introduce identities, fat identities, and use Hubble-Stanton-Lorentz transformation. And these deltas are so-called auxiliary fields, and Now rewritten in this language, you basically minimize the free energy to obtain the gap equations or all these.
These are all done in mean field approach.
These are all done in mean field
That's why
approach.
you don't have the sign process.
Yes. So use mean field approximation to do path integral. So basically, I introduce auxiliary fields, then integrate over them and obtain the free energy, and then I minimize the free energy to get all the equations I want. And, you cannot see it, but when you minimize it this way, you get the gap equation. If you minimize it with respect to the psi bar psi condensate, you recover the previous equation I showed, and then you solve this set of equations iteratively, numerically to get results. So gamma phi is a special case when you are at contact interactions, but we allow for long range interaction. When we allow for long range interaction, gamma phi ansatz, delta 1 gamma phi ansatz is not the correct ansatz. It becomes it's not self-consistent. You see divergence. So what this means is that we need to introduce other gap structures and do it very carefully. And this goes often in the name of multi-channel condensation. And basically we use many more Hubbard-Santana-Witch auxiliary fields to the minimization and get a coupled set of gap equations. And the advantage here is that this is it's not spurious. I don't have to introduce random cutoffs, etc. And automatically self-consistent, and you get the reliable result out. So in our case, because we have a long-range mediator, so the gap ansatz has to be extended to include momentum dependence. And essentially there are 8 gap structures proposed by Bailen and Lau. Bailen and Lau, they only wrote 10 papers in their life, but all are very good papers. One of them was on superfluidity, and for our case, we just have, because we have only single flavor, we just use just the first 3 gap structures are sufficient to retain consistency. And
Bailen.
okay, Bailen and Lau. I think that English, but okay. So in the end, we want to use this gap structure, and still we want to reduce the Lagrangian to something of this. There's a lot of technicalities involved, which I will not go into in detail, but I'll give you the result. So the result we find is that the dispersion relation now has additional momentum dependence due to additional gap structure. So if I'm just in the PCS theory, that is just with the gamma 1, with the gamma phi ansatz, I will just have this term, and then you go back to the curve I showed you before with the band structure. Now because I introduced delta 2 and delta 3, I get additional. And these are the 2 terms that regulate the dispersion relation.
K is the 3 momentum magnitude.
Sorry?
K is the 3 momentum magnitude.
This is the 3 momentum magnitude. Yeah. So these are all translationally invariant. That's the only requirement. And we are breaking Lorentz. So
you're breaking Lorentz.
yes, we are breaking Lorentz. Because finite density already tells you that you're fixing a frame. You break it right away. Okay.
But these kind of relations we have many exotic phases, different condensate, not only the cyber side but also other types of condensate.
Yeah, there could be. So we simplify the problem because what we'll work in only 2 particular directions of this ansatz. One is with the plus combination, and the other is the minus combination. And in these 2 directions, there's only one condensate. If I take another direction, I agree there are other things, but we found that they are not really stable, so we didn't go into it too much. Okay, so I'm very proud of this set of gap equation, although it will not make any sense to you. But the only point here is that we could obtain a momentum dependent gap equation. So I have a gap on the left and a gap on the right. The integral is an iterative integral equation which you have to solve. And having light mediators gives you these log structures. So it's a nice numerical problem, but analytically we are very proud of this because we could get this out very consistently.
So if you get analytical solution, you will be even more proud.
Yeah, but we tried very hard. We couldn't get an analytical solution. We could get an analytical solution in the relativistic limit, but not in the non-relativistic limit. So, not so proud. So in the end, we could. So this is the other direction. So delta plus minus and this kappa is the other direction. And in the end, they all depend on each other, and you have to solve this.
It may be a good idea to put in a box the original PCS gap equation.
Yeah.
So simple and pretty.
Yes. So if I take m phi is very large, and I assume on the right hand side that delta is independent of momenta, I go back to the
Yeah, I'm saying that I put it in a box just to contrast how things are evolved.
so
You have any divergence is coming from omega, which is
so this is k square plus m square. So I'm at finite m.
omega is no.
It's not divergent. Yeah. So okay, I didn't put the contrast, but effectively in the normal BCS was approximately like, so the whole thing reduces to a very simple form. Only this depends on momenta through the dispersion relation. This is omega. So if I'm assuming delta to be independent of momenta, the whole thing simplifies. I can pull this one out, cancel this one, and then get the one and just solve for the gap. So okay.
So for large scale,
Large scale is finite. Yeah.
I don't see what it is.
Can be done on the line. So at large scale, let's see, log goes as k, get log 1. So the only thing you need to worry about is the constant term. And in the constant term, at large k, the k cancels.
Quadratic DKK, the measure is large.
This one.
No,
That one is, but I also have a epsilon is a k sitting in the dispersion relation. There's a square root of k square plus k plus mu square. Plus delta square. Delta is also momentum dependent, non-trivial. That pulls it.
okay then.
Yeah, that pulls it. I'll show you the result. So maybe it becomes a plan. Okay. So first so this is the result we get numerically, and just to here I put the BCS solution. So the BCS solution for the gap really goes like exponent of 4 pi square m pi square g square kf square in the relativistic limit. In the non-relativistic limit, it's just kf square should be replaced with m times k. That's the difference.
That was the excitement, the essential singularity.
Yes. The g square. That's the excitement. Okay, and now because we have a complicated gap structure, we no longer have a simple relation, but numerically we sort of see the exponential, and that is what is shown in this plot here. I have the gap rescaled to the mass divided by Fermi momenta divided by mass. Let's look at the blue curve. So heavy mediator. So this is really the BCS solution, where the mass of the mediator is 5 times dark matter mass. And in the relativistic limit, I really go to the BCS solution. And even when I reduce the chemical potential of the Fermi momentum, I see a nice exponential follow just following this one. And you can play the same game for g equal to 3 or 2. And this is precisely for heavy mediator, we strictly numerically recover the BCS solution consistently. But then, because we did all this work to have a long range mediator, so now I have a m pi over m half, like 50% of dark matter mass, not very light. And for that, we get red curves as a result. So if I go from the left, as I increase the number of particles, I see that the order parameter exponentially increases. Still, in some sense, follows the non-relativistic BCS solution. And as particles become relativistic, there's a sharp jump down and then goes back to the relativistic BCS. So And the same feature is seen for different values of coupling, G equal to 3, G equal to 2. So here, these are all non-perturbative by nature, so we don't care about more corrections. The point is that because of this gap structure, we have a consistent solution that goes smoothly to well-known result, and in between there's a nice transition which we understand. So
This is an exact result.
this is an exact result.
Exactly.
Numerically, not analytically.
But at the mean
It's exact at the mean field level numerically. And on the y-axis, on
that was
the
asked, I guess Raghuveer asked that question. So there are attempts to go beyond mean field, but that's very difficult. In Indian models also people do the mean field. So they get this essential secret shorted as mean field.
so on the right side, I show the different components of the gap, that is delta 1, delta 2, delta 3. Here we wrote it in terms of a particular direction, but then we can decompose it back. And here we see that some of the gaps, so blue curve, the blue one is delta 1. So that is the most dominant Higgs regime as expected by the BCS solution. But then you also have other curves, for example, the green and the yellow, that regulates the low energy part maximum. And that's what gives you. So this was one example. And then we go to a more crazier example where it's not so crazy, but we get crazy things as soon as I make the mediator marginal line, just 10% of the dark matter. And this needs a little work to understand. So let's start with the G equal to 2 curve. So at low density, we find that our numerical algorithm already tells us that we are in a crossover regime. Because this line here is basically Fermi energy at the energy at the Fermi surface minus the mass. And we found the order parameter to be larger than that. That means we are in a crossover regime. But we were very confused, so we went back to the original phase diagram and computed the scattering length. And we found that the scattering length here is indeed positive. So at very low density, so you're actually in the VEC. And as I increase density, you go to a crossover regime, and then particles become relativistic as I increase even more, and then they become, then they go to the relativistic VCS. But a different trend was seen for G equal to 3. When we started at low density, we were in a VCS phase. There was an exponential increase in number density, but then at some point, our Fermi surface was deformed, so we got a very jumping solution numerically, and this we interpret as a crossover regime. And in this regime, we strictly have to recompute the chemical potential iteratively, but we don't do that. By that, we were already sick of this project by then. And then as we increase the chemical potential even more, for the Fermi momenta, it comes back to the relativistic VCS. So this whole self-consistent setup could in principle capture all these regimes very nice. That's the main point. So coming to your question about the K dependence. So here I can show you, these are the momentum dependence of the gap functions. So here the gap functions were only evaluated at the Fermi momenta, but here we give you the full momentum dependence. And as you see, as you go to large K, there's a very large K dependence, which regulates the whole gap equation. And this is what makes it self-consistent. And so the one way to understand this in the contact limit is going through the order parameter versus KFA inverse. So what is happening here is that, at least with the solid curve, we start out in the BCS phase, which is this one, and then your crossover, and then you come back to this. But on the other one, you start out with the PEC phase, which is delta over E. Things are larger than the Fermi surface, so E over delta over EF is large, and then it comes back to the data. So we could understand this through that diagram. But one further step we need to do is how to solve mu also iteratively, which we have not done. Okay, how much time do I have?
5 minutes.
5 minutes. So let me skip the effective range theory maybe. I want to go to the final result in the last few minutes. That is basically the equation of state. So given all that machinery, what we actually want to do for dark matter, because there was no dark matter in the past 10 to 15 minutes, but in the end, with all of that, what we want to extract is pressure versus energy density as a function of coupling. So here, because of the computation involved, I use something called C phi square, which is alpha m square over m pi square. This is what naturally comes out in the calculation. And because pressure is nothing but negative free energy, that's the easy part. And then energy density is m times number density minus mu and so on. So 1 over C phi. So here I'm in, so if C phi is large, my coupling is large. So the pressure here, it means that a very large coupling, the system behaves like an incompressible liquid. That is constant density core. So this predicts core dark matter here. But if I start reducing the coupling, at some point I become a gas, and when I reduce even further, I become a. So the distinction between fluid and gas is pretty weak here. The only reason why we say fluid here is that for a fixed coupling, as I increase the pressure, it just smoothly goes up, doesn't transition into a liquid phase. But what I call gas is that for a coupling, as I increase pressure, it transitions to a liquid. So these are purely words, but at the equation of state level, that's similar. So that was pressure, and now I can show you the number density as a function of coupling. So at small coupling, I'm a fluid corresponding to this region, and at larger couplings, I'm gas. And one sees that there's a coexistence phase between liquid and gas, and that even a larger number density for fixed coupling, you are really at a liquid. At very large coupling, things break down. We get negative number densities. That means something is going wrong, and we interpret this as a metastable configuration. So they are out of equilibrium, and possibly no stable, long-lived solutions can exist in the machine. So that was the main.
What do you mean by coexistence here?
So I have liquid-gas coexistence.
Two-phasing.
Two-phasing.
Is there any surface tension?
I don't know.
Then what is the coexistence? If there is no surface tension, then what is the difference between?
So I don't know. Okay, I skipped over this. I don't phrase it in terms of surface tension because coexistence for me is through Maxwell construction.
What I mean is that if you have an air bubble in water, then there is a surface, right?
Yes.
Yeah. So that means there is coexistence here, right? There is gas and water as well. And if you stay, meaning that kind of coexistence, there should be surface tension.
It hasn't calculated it.
Yeah. There is one. So there are liquid droplets in an environment of gas, and the liquid droplets indeed have a surface tension, but I'm not gone there. We couldn't figure out why it could be useful for dark matter. But
And also you show that there is a larger and larger range of density where this mixture is happening.
yeah. So
Just one point. You look at the velocity of sound.
So we did.
What was your question? I didn't hear it.
Velocity of sound.
So
Yeah, the equation.
So velocity of sound there is square root of delta p over delta rho. So here they are larger than 1. So that things are wrong. Here they are still smaller than 1/3.
You see the actual number might be more useful phenomenon.
Yeah. I didn't make a plot about the plot of this, but we checked whether it was consistent. That we checked.
The sound false.
So in the coexistence phase, there's a step function sort of behavior. Speed of sound changes and then picks up again. I didn't make a plot though. It is not smooth.
This
So,
is the first order phase.
so this is the first order phase transition.
It will be somewhere in the coexistence.
Yeah.
So it's not a crossover.
So
Yeah.
this is not a crossover. So yeah.
And why do you say that region is not equilibrium? Because there the masses are very large. Masses, if they are larger than the chemical potential, then anyway this problem will suffer from single-based problem. There are different other problems.
So there are a few reasons. One, the speed of sound, we were not getting a good number here. We were
That
getting
will be because the finite density calculation breakdown.
yeah,
The mass is larger than mu.
yeah, that's true. Like,
Or there is something else.
so the free energy was not minimized there. Maybe it's related to the same what you said, but in the free energy sense, you could not minimize free energy at the second derivative.
Because finite temperature, then you could have gone there.
Yeah.
Since you are doing at 0 temperature, so mass is larger than the chemical.
Yeah. So, okay, so maybe made it in time. So when you put all these things together, I can do pressure versus density plot for some values of the C5 square. A free gas goes like that. P is rho. P scales as kf to the 4. Rho scales as kf to the 4. As soon as I add interactions, equation of state at low density drastically changes. At high density, they still behave, they follow the relativistic free gas solution, but at small density, you see qualitative change. And this is very important because what we can do now is we can use the pressure and density relation, plug it in Lane-Hampton equation, and see what is mass radius relation one can obtain. And that is shown in the right hand plot here, where mass is in solar masses and radius in kiloparsec. So this is for like some sort of a sterile neutrino dark matter electron voltage. These blocks are typical masses of galaxies and dwarf galaxies, approximately. And the dashed line here is basically when it's a free gas. Here is a free degenerate gas. This is the typical slope you get, like it goes as R cubed in this plane. But as soon as I turn on interactions, the slope completely changes. It increases with R. There it was going as 1 over R cubed, and now it goes as R cubed. So this was an interesting result because having all this finite density effect, you can fit the same model for large galaxies and small galaxies, dwarf galaxies. So that's the main message of all of this exercise, going through various things. In the end, we just wanted pressure and energy density and mass radius relation. We were surprised by it, but it looks like it's a nice fit to both regimes.
So this is mass of what?
Mass of the halo.
So what is the why do you get a relation between mass and radius?
Why?
Yeah.
Because I have the equation
So
of
you
state.
have the equation of state. So
I put it in Lane-Hampton or Tolman Oppenheimer or whatever. From there,
if you exceed that, then you will collapse.
If I exceed that, there are two possibilities. One is probably we never go to those saturation regimes, but if you exceed the critical pressure or critical energy density, either you disperse, form smaller droplets and destabilize the system, or you go to a black hole. These are the two end pathways. And this line is the stable solution, far away from those regimes. So basically, particle is still not relativistic. Somewhere here, this red curve corresponds to this red curve. So it's somewhere here. So for an energy density, the pressure is lower than in the free gas.
So if it's standard WIMP, you think of it as a free gas.
Yeah.
Then that would be the dashed line.
This would be the dash. So we have to be careful here because in the standard scenario, structure formation, small structures form first, they merge to form bigger structures. That's the WIMP thing. So if I take whatever 100 electron volt mass, initially it might form some mass like that, but today it would have evolved to larger masses. But the point of finite density effects in this model is that the initial mass itself nicely placed. So it's more like a warm dark matter scenario where structure formation is inverted. So you form bigger structures first. And that is what we see here as well. So qualitative.
What is the size, what is the mass of the smallest dwarf galaxy? Is there an estimate?
It's about 10 to the 6, 10 to the 7 solar masses.
Cannot be lower than that, or the idea?
So astrophysics classifications can be murky. And the upper limit is well known, or somewhat is consensus, but the lower one is not clear because there is ultra diffuse dwarfs, which is unclear whether they're truly dwarf galaxies or not. There is some gray zone in this area, so I cannot say more about it. So in the end, yeah, but typical number you would like to keep in mind is about 10 to the 7 solar masses, 10 to the 8. For about kiloparsec.
From your analysis, what is the statement? I mean, you cannot have a smaller radius, a smaller mass of this object. It ends somewhere, right? 10 to the 7. It begins at 10 to the 7.
No, so this curve goes like on the way.
Oh, it goes on.
Yeah. But so these are the observations. So we just cut it off there. But the slope doesn't change, just observe. So for sure, surely there are structures of that form observed in the universe. But there is debate of whether these systems are dark matter dominated or not, and things like that. So we can go there. So, okay, then let me skip over this. So this brings me to conclusion. Interestingly, if you assume finite density and recycle finite density QCD to dark matter, you will see that emergent phenomena can be realized in dark sector, and we delimited phases of the Yukawa theory for the first time and developed a formalism for computing momentum-dependent gap equations. And with all that, we constructed the equation of state, from which we obtain mass radius relationship. So there's some lot of future work in this direction. Basically, if you notice that I did not put the lambda pi 4 in the Yukawa theory, probably it should be there. There's nothing forbidding me, and it changes things drastically. Could change things drastically. We do not know. It's a more difficult calculation in progress, and now we also want to match on to actual data. Like there are a lot of dwarf galaxies. We want to see how it works. So the picture is there a core of these condensed phases in the center, and then as you go outwards, maybe you are more diffuse Maxwellian-like particles. So that can be tested with data, and we are compiling that data to match on to these.
You do that. The file of this.
Yeah.
How would you do that?
Sorry.
How would you do that, and how would the experiments do that?
So you measure motion of stars, and from there you can extract gravitational potential, and from that velocities and velocity dispersions. And then, so you can construct theoretically a profile that can have a core in the center and gas-like
So you match
outwards.
the profile to the
Yeah, and see if such a thing can be matched in the first place. And if it can be matched, that would imply a restriction on some of the model parameters. And that's the direction we are going. So,
They say there is this core cusp problem.
yes.
In relation to the dwarf galaxy. How do the density goes close to the center and how far it goes?
Yeah.
Will that solve the problem?
No, this story predicts a core. Okay. Like a liquid phase is like a constant density phase. So it's a core. So it doesn't solve the core cusp debate, but it just predicts a core profile. In the liquid phase. If you're gaseous phase, you can be cuspy, but in the liquid phase, you're core. So basically, that's all I wanted to
Does
say.
it put a limit on the mass of the whatever dark matter can
In principle, yes.
Sure.
We're in the process
you
of.
have any number for that?
Can't say with confidence yet. So I can say something with not with confidence. So typically from dwarf galaxies, you can, without interactions, you can constrain KEV mass.
KE.
Yeah. But with interactions, you can reduce it a bit.
with lambda, completely change.
With lambda, things can change because now you have, if you have a lambda pi core, I'll have another gas. I have a self-interacting scalar that will also behave like a gas. So my equation of state should also include that effect. So there could be some changes, some drastic, depending on what I choose for lambda. So that's all I wanted to say. Thank you.
It's dark matter. So there are structures of dark matter, right? Like ordinary luminous matter.
Yeah.
So they may have started forming at some point of time in the early universe. How that compares with the luminous matter structure?
So the main point,
They would be same or different, and if your calculation has any, conflict or consequence for the CMBR type result, which try to pinpoint
So it's essentially a galaxy without normal matter. It's fully dark matter.
So there can be galaxies with only pure dark matter.
No, yes, sure, but we can't see that.
No, it will affect
That's a very-
curves will be affected, and also
Yeah.
gravitational density will be affected. They will
Yeah.
gravitate.
They will gravitate. But coming to your question, so the main difference between normal matter and dark matter is that normal matter comes with photons, so it can emit, lose angular momentum and form disks. And these disks are formed inside halos of dark matter, which are more spherical, which do not have a light quanta to lose angular momentum.
But
So-
still they couple to graviton, right? And there is recently there are
yeah, it couples to graviton.
microwave background from gravitons.
But the rate at which you can emit a graviton is a Planck suppressed. It's not sufficient to collapse to a DC, first of all. And that's one of the main differences between dark matter and normal matter. And on top of that, the dark matter structures form earlier than baryonic structures in the earlier phase. So all baryons you have are sitting inside dark matter halos today. 95%, 99%.
So dark matter is basically seed for this structure.
Yeah, exactly. Because they provide a deep potential well and all baryons will follow. This
It closes that. Normal baryons are inside the dark matter structure as well.
But what is this density fluctuations in inflation seeding this structure?
that is different. There will be density fluctuations. So they will see. So that only there is. They say it's matter over density. So there are matter over dense regions and under dense regions.
Yeah. And that seems to agree well now.
Yeah, and matter is dominated by dark matter. So over densities and under densities are basically more strongly, at least applies to dark matter 5 times as more as normal matter. So that's.
So the density fluctuations are the seeds for the dark matter collapse. The dark matter collapse is the seed for baryonic matter.
That is all the missing satellite followers. Like you said,
So in my mind, missing satellite is not a problem because with better and better observation, if you look up a plot of how many dwarfs you have observed over time, this is increasing. It only tells us that they are faint objects which are not yet seen. And the only thing it does is it predicts even more. It predicts lesser dwarfs because this predicts cold profile, more like warm dark matter. It predicts lesser, smaller objects.
So does it have any constraint from large scale power spectrum like millimeters? Or do those scales at all?
I don't know because these are very small scales. Power spectra still constrains megaparsec scales, so still galaxy level. So power spectra tells you what is the interparticle distance between collapsed objects, and that is about megaparsec. To test this, you need even smaller information at even smaller scale.
So the deviations will start appearing only at the scale of galaxies.
Yeah,
But not larger scale.
not larger scale.
Any other questions?
Suppose dark matter is a superfluid. Is there any dynamical implications? Things like zero viscosity.
Things they are supposed to change the local velocity. Is what
but any qualitative change.
So at least, okay,
Because superfluid or superconductor is something macroscopic quantum, it has profound consequences.
Yeah, yeah.
So I wonder if there is a superconductor sitting there,
it's a question of scale.
Superfluid.
superfluid.
So it's a question of scale.
Not in the scale of halo.
Yeah. So even if you're superfluid, so for fermionic dark matter or fermionic particles, the correlation length is very small. So even if you're superfluid, there are like chunks of superfluid. The correlation lengths are not kiloparsec.
But that depends on the mass of the fermion.
Depends on the mass. Depends on the mass of the fermion. And what I have in mind is order 100 electron volt of particles.
But they have a short Cooper let's say, long distance implications, superfluid flow, flux quantization, various ramifications. I wonder if there is anything, because you are talking about a quantum object at weight dwarf level,
So
quantum. So I wonder if
Dwarf galaxy, not
dwarf galaxy, sorry.
So there is one observational prospect where you can say something, but it's very speculative, borderline science fiction. So
As if it's not speculative.
there's speculative or speculative plus. So
with some calculations.
So let's say I have two galaxies which are superfluid,
Yeah.
and they're merging,
Oh, then there can be Joseph said.
and then there is vortex formation.
Okay, so that's what I was saying. Because it's not a speculation, it follows. Once you have superfluid.
No, two dwarf galaxies.
Yeah.
Dwarf galaxies can be superfluid.
Yeah, and when they will merge, you can see something. Basically, the vortices, and that throws around particles, throws around known objects in a particular node.
You never come close to this unitary gas regime.
No, but unitary gas regime is excluded for dark matter. I skipped over that, but
That would have been more interesting.
yeah, but as soon as I put in the bullet cluster limit, it precisely kills that. Because if bullet cluster tells you cannot interact too much. So we are part of it. Unfortunate, but that's how it's.
Well, just one suggestion. All these calculations, these new structures that you're talking about, for example, maybe cold atoms can test this. Because cold atoms have experiments have seen BCS crossover with respect to cold fermions. So they have seen one crossover effect. According to you, with the increasing phase shift and so on, there should be many.
When you go to temperatures much lower, there's a nanokelvin and that will be needed.
No, but it's a question of interaction. If they can do.
Yeah, that is
So please talk to cold atom people. They may get excited.
Yeah.
There are cold atom people in Italy.
I know.
But sorry, these effects, are they relying on electromagnetism or independent?
See, cold atoms is fascinating. Just take atoms,
structure of that.
collect at least million of them, trap them in some optical lattices.
Yeah, but that's all
Hyper-
electromagnetic, right? I mean, you have an electromagnetic lattice in the traffic. But here, it's
No.
not coupled to our electromagnetic,
No.
right?
Lattice can have just cold atom as post condense, fermionic molecule, Fermi surface, like as if it's in free space.
But here you are considering the Yukawa potential. Can that be?
I'm talking about simulation. Anything that you do.
No, my only question or comment is if it is coupled to, if the probe requires coupling to our electromagnet, this cannot happen. Right? There is no U1 coupling to our
No,
electromagnet.
this is spin-spin interaction.
See, anything can be simulated.
The observations you're talking about, the probes, should not go through our electromagnet.
No, it will
No,
serve
but
as
it's
analog.
simulated. So it's we will see through our
No, what he said.
How will we see it?
No, what he says is
We'll
it might be analog model.
analog.
Yeah, it will happen in the dark sector, but how will we see it?
This calculation, model degree matter. What are you calculating?
See, the mathematics of this and cold atom.
That's right.
That is irrespective of
Whole, that structure is all there, and through
Exactly.
gravity you can feel it, right?
Anyway, we
You
can discuss
see it
it.
only through gravity, but not otherwise.
So okay, for cold atoms, for example, Bose-Einstein condensate was made with rubidium atoms, and how they do it is they tune the scattering length through electromagnetism.
That's the resonance.
So that is preparing a ground state. Now I think what he's suggesting is that if there's a spin-spin coupling or something with dark matter, so like a liquid droplet which has a spin, that will interact with this bound state. And probably it'll detune or something, maybe you can pick it up.
You pick it up how?
Spin-spin interaction.
Yeah, but you have to couple to it, right? What will you couple? It
There's no
doesn't couple to our
There's no
electrodynamics.
coupling
How
to
will
the
you
dark
couple?
matter.
No, what
There
I'm
is a
saying is,
coupling and cold
mathematics is
atoms.
here.
Cold atoms, there is a way to tune the coupling.
That's through electrodynamics.
Okay, the dark matter.
Okay, we'll talk about it
Talk
later,
about
so you should
lens is very.
So
I was going to ask, are there any implications to direct detection in all of this?
So the direct detection, if you're in DEC phase, it suppresses direct detection rates because now you have, instead of one WIM, you have a molecule of WIM. And when it's scattered, there's a form factor that will suppress the scattering rates.
But the mass,
The mass will also
you
be
compare
different.
at the same mass.
Let's say I'm at the same mass, but now I add a form factor. So this basically changes your spectrum or recoil spectrum and suppresses scattering rate. That's the implication for direct detection.
So what Shayanta was asking, you have done it for mean field. So, but to go beyond that,
I don't know how to.
You have to do it in
That's future plan.
Which structure?
Okay, so we'll end the thank Raghuveer again.
Thank you.